Good morning, everybody. Hi, Lydia, and
Hello, Lydia.
welcome back to Galois Theory. Plan for today is we're going to talk some more about polynomials, and then get into our next packet, which will be on irreducibility criteria. Yay! Usual office hours next couple days. Homework 3 due Thursday. So, a couple things. One, there's not going to be a homework due next week. Homework 4 will be due Tuesday the following week. Why? Because I have ideas for what I want to do on homework 4, and it kind of requires stuff that we're not really going to talk about until late this Thursday, getting into next Tuesday. Homework 4, by the way, going to be very example-driven. Lots of examples of, here's a polynomial. Is this irreducible? How do you know? I haven't finished grading the homework due yet. Deal with it.
But they're so cute.
Yeah, well, that doesn't mean other things don't come up.
Fair enough.
Like having to spend half the day trying to persuade Dr. Trelaw to let me have linear algebra in the fall.
He was going to take linear algebra.
Well, that change is needed to be made. Anyways, that's a different discussion. Anyways, figuring out what classes we're going to be offering in the fall. Stay tuned for fun. Once that's out, I'll go through my usual discussion of, here's Dr. Driscoll's thoughts on what you should be taking.
I am in fact taking multivariable calculus.
Good job! But that does bring up a question, is everyone here taking multivariable?
Yeah.
Except for Sam.
I was to say, well, or is currently in the process of taking. Lydia, how about you? I know you have, I'm just kidding. Okay, so, good. Alright, you want a sneak preview?
I don't get to.
Aw. Surprise differential equations, I think is going to be offered in the fall. Mathematical logic, complex analysis. Topics course, in quite like a possible topics course in cryptography.
Oh, I want to take that.
No, you don't.
Yes, I do.
Me.
Yes, that's right. Why do you keep making good topics?
I can't help it. I'm just saying. Okay. All right, let's get back on topic.
Can you take a topic course?
Got a lot of seniors in here. This is irrelevant for, anyways. Last time I started trying to prove this theorem and kind of got flustered early on because you all were heckling me, and because so I looked over the weekend at my notes and realized I just needed to include one more small case and that everything was correct from there on out. So thanks for that.
You're welcome.
So, without further ado, let's prove that if K is a field, then the ring of polynomials over K does form a Euclidean domain. Yes, Parker.
What is the joke of the day?
Oh yeah, I saw What?
I have a joke.
Oh, let's hear yours.
What's purple and commutes?
Oh, I know this one. Oh, this is a Gabler classic.
An abelian grape.
Nice. It's one of Dr. Gabler's favorites. Mine was, oh look, Dr. Fuller is walking down the hall with a sheet of graph paper and an evil smirk. I think he might be plotting something, but I like yours better. Thing is, I usually share your joke of the day with my 105 class, and which means that limits how much actual math can be in the joke of the day. But if I were to tell them that one, for instance, they would have no idea what that means. But I do that. All right, so here's our idea. We're gonna let K field starts the same as it was last time. We're gonna let f and g be polynomials with g not equal to 0, and we need to define a delta function, which, no, it's not degree, but it's strongly related to degree, where our main goal for this proof is going to be to find, given our f of x and g of x, we're going to find some q of x and r of x, where the that we can Euclidean algorithmize, meaning f of x is equal to g of x times q of x plus your remainder polynomial, where your remainder polynomial needs to have smaller degree than your original g of x. All right, y'all ready for this? It's going to be a proof by induction, meaning we're gonna induct on the degree of f of x specifically. So we're going to have a base case starting off with f of x having degree 0, and show that if f of x has degree 0, we can directly prove this. And then from there, we'll assume it works for all f of x of degree less than some n, and then prove that if the degree of f of x equals n, it must also work for that if it works for all smaller values of n. And from there, induction will tell us that it has to work for no matter what the degree of f of x is, and thus give us our result. So that's where we're going with this. So first of all, base case. If the degree of f of x equals 0, well, that's the same as saying f of x has to be an element of our actual field. F of x is a constant polynomial, meaning it's just an element in K. Then the result holds. As how can we define our q of x and r of x if f of x is constant? This is where I kind of got tripped up a little bit last time, and it's because I didn't consider the fact that you actually need two cases. One where g of x also has degree 0, and one where g of x has strictly positive degree. So let's start with the degree of g of x is also equal to 0. Meaning g of x is going to be an element of our field K. Then how can we fill in our blanks in that case? If f and g are both degree 0, meaning they're both just elements of the underlying field, how can we pick some values for q and r in terms of f and g that'll satisfy this equation? Hint, g of x is in the field and it's non-zero.
We can just let q equal fg inverse.
Yeah. Just write it as f over g. Yeah. G's in the field, it's non-zero by our starting assumption, so it has to have a multiplicative inverse in K. And then what's our R?
0.
Remainder term has degree negative infinity, which is less than 0. So that case is pretty simple. Second case. The degree of g of x was greater than 0. Then we need to fill in the blank a little bit differently, because if degree of g of x is greater than 0, g of x isn't going to have a multiplicative inverse, so we can't just take f over g plus 0 anymore. But keeping in mind here that the degree of f of x is 0, what's another way to fill in our q and our r in a way that'll satisfy this equation? And we rest.
0 and f.
Let's put 0 in f. Why? Well, 0g plus f is certainly going to simplify down to f. And here, we'll have that the degree of r of x is the degree of f of x, which is 0, which is certainly less than the degree of our g of x, which is the condition that our r of x needed to satisfy. So between these two cases, that handles everything where the degree of f of x is 0, meaning f of x is a constant polynomial. Any questions or comments about either of these? Just, we need it to be different in each case because we need to make it so that no matter what our r term is, our remainder term, our r of x, here I just wrote r and f because they're constants. Our r of x always needs to be some polynomial of degree less than our g of x. Okay, so that's our base case. So now we're going to do our induction step. We're going to suppose this process for all f of x with the degree of f of x being less than some fixed value n. And now we need to suppose that f of x has degree n and show that if it works for f of x's that are of smaller degree, then it has to work for degree n ones as well. Everyone on board? So now we can show that we can find a g of x and q of x, or not g of x, a q of x and r of x that will get the job done for a degree n f of x. We are PG. So how do we break this? How do we break this down into finding a g of x and r of x in this case? Q of x and r of x, so many variables. This time it's a little bit harder because it's not. I don't think there's necessarily an obvious formula. If the degree of g of x is greater than the degree of f of x, it's not so bad. Then we can fill in our blanks without too much trouble. If g of x is a polynomial of degree greater than n, how can we fill in our q and r here? Yeah, same way that we did down here. Just let our r of x term be f of x, and our q of x term could just be 0. So we've eliminated that case. There's a lot of cases in this problem, as you can see, or in this proof. So we can assume then that the degree of f of x is strictly greater than or equal to the degree of g of x. And now comes the fun part. Because we somehow need to use our inductive step up here, the fact that it works for polynomials of degree less than n, to show that for our f of x, we can find a q of x and r of x that'll get the job done.
So if we multiply g by whatever we need to get, like for example, if f was 3x cubed and the largest degree of g was 2, then we multiplied by 2x to get to 3x cubed. And then subtracted it so that we had a result that was less than n.
Yeah. Well, not necessarily. I don't think we necessarily need to multiply by 2x. It depends on whatever our degree 2 there is. But multiply by something x. Great. How does this process generalize for an arbitrary polynomial in an arbitrary field?
That I'm not so sure about.
Yeah, it's not so bad to do if we're looking at specific examples. You could just do polynomial long division. The problem is, we're working over a ring where we don't know we can do polynomial long division.
At least we only have to do it once, because we have every smaller n we know works.
Well, you say that.
Well, we're assuming it.
Yes,
so.
we've done all these smaller cases. So we're gonna have to do something a little bit sneaky here to find our q and our r. So we're gonna suppose that f of x and g of x have leading terms a sub n x to the n and b sub m x to the m respectively. So f of x and g of x, we don't know what exactly they are, so we're gonna assume. So we're just gonna say they have to have leading terms that are non-zero. That's guaranteed because g of x is non-zero, and f of x, well, we're assuming f of x is non-zero, because if f of x is 0, then, I mean, this case handles it. So we're assuming f of x and g of x are non-zero, so they have non-zero leading terms. Meaning n here is going to be the degree of f of x, and m is going to be the degree of g of x by construction. And now we're going to define some new polynomial. You ready for this? It's not going to be q, it's not going to be r, it's going to be something different. We're going to define h. We're going to define h of x to be f of x minus a sub n divided by b sub m, x to the n minus m, all of that times g of x. Holy Toledo. Yes, Eleanor?
Well, then your leading term is going to match f of x.
Yeah. What's the leading term in here?
It's going to be x to the end. Or a sub n, x to the end.
The leading term is going to be a sub n x to the n, because you just, when you're multiplying two, the leading term of the product is the product of the leading terms with two polynomials. So since the leading term of g of x is b sub m x to the n, if you multiply this by that, you just get a sub n x to the n. And if we're taking f of x minus that, the leading terms are going to cancel out. So you get something where h of x has degree less than f of x. Then the degree of h of x is going to be strictly smaller than the degree of f of x, which we said was n. So if h of x has smaller degree than n, what do we know we can do with h of x?
This process.
This, yeah, we can do this, because we assumed we could do this process, meaning find a q and an r, that'll work for any polynomial of degree less than n. H of x is a polynomial whose degree is strictly less than n. So we're going to apply this process to h of x. And that'll give us not q of x and not r of x. It's going to give us a q1 of x. It actually will give us our final r of x. Watch it. So we can then say, by assumption then, there exist, I'm going to call them q sub 1 of x and r of x, such that h of x is equal to q1 of x times g of x plus r of x, where the degree of r of x is strictly smaller than the degree of g of x. So we're applying the process to this polynomial of strictly smaller the degree than n.
Should be r sub 1 of x.
Nope. Well, I mean, it can be, but it turns out the r of x we get here is going to be the r of x we want for our final result. We're not going to get our final q of x, but this is going to turn out to be the final r of x that we want. So why is that? Well, now we can actually, once we have a q1 of x, we can actually define the q of x. That's going to be the final one we're looking for. We're going to let q of x just be q1 of x plus a sub n over b sub m x to the n minus m. And Jonah, that will be the final q of x that we need. Then we just have to show that the q of x and the r of x that we have produced actually get the job done. What does that mean? We just have to show that if we take q times g and add r, we'll get some mess that simplifies down to just f of x. Any questions or comments thus far? This is kind of a messy and complicated proof, and I realize that, and that there's a whole bunch of variables floating around, but what we've ultimately done is we're given an f and g, we want to find a q that fits in this blank, and an r that fits in this blank, and the whole process thus far has been producing a q and an r that we'll show in a second satisfy this equation. Elmer?
So suppose this process works for all f of x with degree f of x less than x. Is that the induction step?
That's the induction step, okay. Yes. And so the induction step we're applying to this h of x here, which you actually showed has degrees less than n. So,
yeah.
So it falls into this category of things where the process works.
Okay.
And
so when you have q1 of x here, is that like, does that q1 of x represent like, okay, wait, actually.
The q1 of x is what this process spits out for the h of x. So basically this process says given any h of sufficiently small degree, and given our g that we defined earlier, there are things that we can fill in here that will be some q sub, I'll put a q hat and an r hat that will satisfy this equation.
Why can't you just like throw in h of x as the q of x? Because it seems like over here on the right side, if you were just multiply it out, like,
why can't this just be q of x right here? Because if I took this multiplied by g of x and added this r that we get here, it wouldn't simplify down to f of x.
but I'm just seeing here on this right side that g of x, if you multiply it out, it's going to end up being to 0, right? H of x?
H of x would be 0? The leading term of h of x would be 0, but there's a lot of other stuff that wouldn't cancel out, unless f of x and g of x are the same other than their leading
If
terms.
g of x is the, what do you call it?
The divisor, the thing you're dividing by.
Is the bm x to the m.
That's the leading term of g of x. That's not all of g of x.
That's what you're saying, yeah.
Yeah, sorry, a lot of pieces here, but yeah. This is not our f of x by itself. This is not our g of x by itself. These are just the first terms if you were to write it out. F of x and g of x probably have a bunch of other terms, unless we're in a really nice and simple case where our proof wouldn't need this level of detail. Any other questions? So now all that's left is proving that, showing that this holds for the q and r we've produced. So if we take, you can see why I got flustered last time.
Yeah.
If you take q of x times g of x and add that to r of x, well, what are we going to get? Well, first thing I'm going to do is I'm just going to swap out our q of x with this formula here, which will give us q sub 1 of x plus a sub n over b sub m x to the n minus m times g of x plus r of x. I'm going to use some distributive property to distribute g of x to each of these terms, which will give us q sub 1 of x, g of x. I'll move the r of x over as well, plus a sub n over b sub m x to the n minus m times g of x. So here I'm just distributing out the g of x to both of these terms, and then putting the r of x in the middle for, I don't know, no particular reason. Where are we going with this, Elnar?
q1 of x times g of x plus r of x is what we defined f of x to be?
Nope.
No?
That's
Where
h of x.
H of x. No.
That's h of x.
Oh, right, yeah. And then,
Yeah, that's just gonna be, all of this is just h of x, if you look up there. So we're gonna get h of x plus a sub n over b sub n x to the n minus m g of x. But what's h of x, Dr. Gerstle, before you erase it? Well, h of x we just defined to be f of x minus blah times g of x. So we'll get f of x minus a sub n over b sub m x to the n minus m g of x plus a sub n over b sub m x to the n minus m g of x. Swoosh! Swoosh! What do you know? It's just f of x in the end.
whoa.
So in other words, we have that f of x is in fact equal to q of x, g of x, plus r of x. So we've proven, not the theorem, but the part of the theorem that said goal at the start, by induction. So, if you look back at our goal was given f of x and g of x with g not equal to 0, we need to find a q and an r such that f equals gq plus r, where the degree of r of x is less than the degree of g of x. By the way, we know degree of r of x is less than degree of g of x from the process. The fact that we had the exact same r of x for h of x as we are for f of x in the end, Jonah, is kind of important because the fact that we have the same r of x means we know that it still has degree less than g of x, which is the condition that's necessary. Any questions or comments thus far? So we still haven't actually proven that k of x is that polynomials over k is a Euclidean domain, because degree doesn't work as our delta function.
Ooh. Oh, right. But it basically
It basically does. It basically does ain't gonna cut it. So why can't we just let our delta function be equal to the degree? Didn't the delta function need to satisfy for all f and non-zero g there exist q and r such that if f equals gq plus r, where delta of r is less than delta of g?
But what about negative infinity is not greater than or equal to 0?
Holy smokes, it's not equal to 0.
and we need delta. Yeah.
Since we need delta of 0 is equal to 0, but the degree of the 0 polynomial is negative infinity. So does anybody remember what we said last time we could do as our trick for finding delta? Lincoln?
2 to the degree of x.
Yeah, it doesn't even have to be 2. 2 is what the textbook uses here, but you could say 3, you could say 4, we could say any positive number really to be. Well, it has to. Well, it can't be any positive integer would work because we need because delta has to always return integer values.
Oh, yeah.
So we can just let delta of f of x equal 2 to the power of the degree of f of x. And then we would get delta of 0 equals 2 to the negative infinity, which we're going to do a little bit of hand waving here and say 2 to the negative infinity, oh, yeah, that's just 1 over 2 to the infinity. That's 1 over infinity. Yeah, that's 0. Yeah, if calculus has taught me anything, it's that little over big equals little.
Yeah.
So there's a little bit of hand waving here. If you really wanted to, you could do like limits and make this more precise.
Yeah,
I mean,
just say
you could
lumpy
just-
call and it works.
You could just define delta to be like,
Okay, no, that doesn't work for a variety of reasons. But sorry.
if you really wanted to, could you just say like delta is 2 to the degree f of x unless the degree f of x equals 0, in which case it's just 0.
Yeah,
Like,
but
unless the degree
then
is negative.
yeah, but then showing that delta of x still satisfies everything else you need gets messier.
Okay.
Basically, then you would need to break up the rest of the proof into like more cases.
We
And-
already have
And I'm already sick, and I want to be done with this proof.
Okay.
So we're just going to do some hand waving here, say 2 bit. And I'm not going to go through and formally prove this, but you can if you want as an exercise. And the rest of the proof still works. Where you basically are replacing degree with 2 to the power of degree, and everything still pretty much holds out.
You say pretty much, but does that mean that you're omitting something?
Yeah, I'm omitting a half hour of taking the time to check something that's really just tedious and not particularly
We've got time.
exciting. No, we don't. Well, I mean, can we today? Sure. That means we're not doing a half hour of more interesting things later on, Parker. I've already given this proof more time than I wanted.
It sounds like an unhealthy relationship.
It is! It's traumatized. You don't know.
Oh.
It's like, where did I go wrong? Oh, wait, it's just this one thing. Yeah. So, any questions or comments about this proof? Just induction and good old-fashioned Euclidean algorithm and getting messy with polynomials and variables and such. Doggy?
I heard clicking, but I don't know.
Oh yeah, Min's around this morning. So, here's a side thing that's not listed in the packet, but I thought is interesting and relevant enough, I think, to discuss. The Q of x and the R of x that we got in our goal, turns out they're unique. Turns out there's only a single Q of x and a single R of x of degree less than G of x that'll give you that equation. So this is not part of the proof anymore. This is proving a different thing. I'm just going to claim that Q of x and R of x are unique. Which is kind of nice. It's like saying if we like to be able to say if I were to divide some number, Isabel, like 7 by 3, it'd be nice to say, oh, here is the quotient, here is the remainder. Not like, oh, we could get some other quotient, some other remainder. No, it'd be nice to have a single quotient and single remainder when you're doing your division, right? Yes. Jackson? Pete? Emily Rose? Everyone's nodding that I care to ask. I'm been asking. Yes?
Is this the unique, like the factorization? Or-
No, this actually is unique. Well, unique as elements of the polynomial ring K of x.
Okay.
I mean, if you're working in some larger field, then maybe there's more, but
Do you have some other delta function? Could you get a different Q or?
yes. If you have a different delta, you could get a different Q and R. Are unique with respect to this delta function. Really, with respect to the condition that the degree of R of x has to be less than the degree of G of x. That's what's really important. Because otherwise, you could always just let R of x equal F of x and Q of x be 0 and boom. That would always be a solution. But that wouldn't necessarily satisfy the remainder condition, the fact that degree of remainder needs to be smaller than degree of G of x. We're dividing by. So this is actually fairly straightforward proof. I like this one a lot. This one's a lot cleaner, I think, than the one we just did. So, how do you prove something's unique? That's a general rule of thumb, because we haven't had too many of these this semester. Iris?
If there are two things that work, they're the same thing.
Yeah, suppose you have two of them. Well, in this case, we're going to suppose we have two Q's and two R's, and then show that the Q's and the R's have to be, well, the Q's have to be equal and the R's have to be equal. So, suppose f of x is going to be equal to Q of x, G of x, plus R of x, which is also equal to Q prime of x. Now that I'm writing this out, I don't like the primes, because it sort of implies there's derivatives going on, but that's not the case. Let's do hats. G of x.
Sorry, specializing you for hats.
There is.
Maybe it's like
Yeah, well, yes, there's
Q vector x.
pretty much any notation you can imagine, there's a special case where it means something specific. But in this case, hats probably trigger less mental connections to you than the primes would.
What should we have mental connections?
Oh gosh, that would be annoying.
Exactly what I tell you to. Alright. Where the degree of R and R hat are both less than the degree of G. So let's assume we have two different sets of Q and R, a Q and R and a Q hat and R hat, that both satisfy the equation we want, and that both have remainder terms with degree smaller than G of x. And we need to prove R equals R hat and G equals, or not G, and Q equals Q hat.
How can a unit vector have a degree?
How can a unit vector be even that? The hat, shut up. Alright, so how are we going to do this? Well, let's start by, well, how do you show two things are equal? You take their difference and show that the difference is 0. So let's take R of x minus R hat of x. Well, if we solve these kind of two equations for R and R hat respectively, we're going to get f of x minus q of x g of x minus f of x minus q hat of x g of x. Just kind of solving these two equalities for R and R hat respectively. Eleanor, what cancels out? Swoosh, swoosh. So we'll get something like q hat of x, g of x, minus q of x, g of x. And now I'm going to factor out a g of x to get q hat of x minus q of x all times g of x.
The degree of R is less than the degree of G.
That's essentially what we're going to get. Well, let's take the degree of both sides of this. Then the degree of R of x minus R hat of x is going to be equal to the degree of q hat of x minus q of x times g of x. Somebody remind me, we have a degree of a product. So if A and B are polynomials, what's the degree of A times B? Andrew?
Degree of A plus degree of B.
Degree of A plus degree of B. So this is going to come out to degree of q hat, q hat of x minus q of x plus the degree of g of x. Everyone on board so far? I think now would be a good time to remind you that the degree of r minus r hat has to be strictly less than the degree of g. Why? Because r and r hat have degrees strictly smaller than g. And if you add two polynomials, you're never going to make the degree bigger than both of the original polynomials. So what do we have here? So that tells us that the degree of g of x is strictly greater than the degree of q hat of x minus q of x plus the degree of g of x, which if we subtract degree of g of x from both sides, tells us 0 is greater than the degree of q hat of x minus q of x. But wait, how can q hat minus q be a polynomial of a negative degree? How many polynomials have degrees strictly less than 0? Isabel?
1.
Which is?
0.
Yeah, so the only way this can happen is if q hat of x minus q of x is 0, which means q hat of x is equal to q of x. And once you know that q hat and q are equal, I'll let you fill in the rest, but that pretty quickly tells you r hat has to be equal to r as well.
So in this case, we use the degree instead of the delta function.
Correct. They're unique with respect to, when I say they're unique with respect to this delta, fine, with respect to the degree. Since delta is like a one-to-one function of degrees, it doesn't matter. So q of x and r of x turn out to be unique as elements of our polynomial ring. If we didn't have this property, by the way, that degree breaks up nicely over this property, that degree breaks up nicely over products like this, which doesn't necessarily hold true over, say, a non-integral domain, then we wouldn't necessarily be able to derive this result.
This also works with the del function, because if you did 2 to the degree of
Yeah.
x, it would just be 1, and then.
Yeah, I mean, if you did this with the delta instead of, it's just slight change in notation, but it comes out to basically the same mark. All right, whew, that was a lot.
How do we know that the degree of g of x is 0 again?
Well, we know, but I just subtracted this from both sides of this inequality. Or you mean like up here? Like how do we get from here to here?
I'm good. Yeah.
You're good?
I thought you could just, I didn't see the plus on the outside.
Ah, gotcha. Yeah, here we just subtracted this from both sides, gave it the old swoosh, 0 is greater. We're left with 0 on the left, degree of q hat minus q on the right. All right, you all look like you could use a bit of a breather. Dyson, can you use a bit of a breather?
Okay.
Jonah? And who cares what you want? All right, let's start off. All right. Start off simple. I'm going to give you 3 different quadratic polynomials and ask you to factor them.
Yay.
You all think you can handle that?
I love
But-
Over the reals.
I'm going to ask you to factor them over the complex numbers, over the reals, over the rationals, and over the integers.
Um,
okay.
No.
What?
Why do you think you do algebra? I'm not supposed to do algebra.
I don't know why am I doing algebra in an algebra class.
That's not fair.
Lincoln, I'm not going back there to give you one. Lydia, here's yours. It's on campus. All right, so take a minute, talk to your neighbors, and see if you can determine over which rings are each of the following three polynomials irreducible, which is equivalent to saying which ones can factor into smaller degree terms. Why is my answer sheet just such a And third one's the easiest. Lydia, do this too. Don't just skip ahead in the video.
Do you think you might have taken too long to say that?
Say what?
Do you think you might have taken too long to say that? Because she would have.
I probably, yes, and I realized that as I was saying it, but I said it anyways. As always, if you feel stuck, talk to your neighbors and or flag me down. Happy to give you some tips.
So I have a reducible. I factored this one, but
Hint, quadratic
there's
formula.
probably an easier way to write it.
Quadratic
You
formula.
guys should bother. I mean, that's what I was going to do.
What is that?
So it would be
I
irreducible.
just used the quadratic formula, and then I plugged it in verbatim.
Oh lordy, that is chunky.
So that's why I said maybe there's a nicer, prettier way to write it, but
Sorry, you could I mean something like this.
yes, that.
I don't like that. My favorite.
I ended up doing complete the square.
The first one of these?
1/4.
Why is that?
It's only factor over.
I just plugged it
I
in the
wanted-
formula.
Imagine that.
I got
Imagine that.
Yeah, that didn't even intend on that one being.
Okay, it's fine.
You do
Yeah, see that.
You got the steps? Cool, cool.
That makes sense. I see.
And if you finish these three early, start thinking about what do you think is the relationship between being irreducible over C versus R versus Q versus C. As I assure you, we will be drawing some fun connections.
I love drawing.
Yeah, see? Here's a connection. Woo, I've connected these two things with a double arrow. Connection.
Oh no.
You broke it.
Because I didn't like that
like my beard.
No, I do like your beard. It's like I think it's most similar to mine.
These two things equivalent.
I like that. I think this is a good quality.
I had to take a closer
What
look
do
at
you think,
Jackson's real quick. But
Seamus, no.
Are these two
Next
equivalent?
one, similarly outrageous to real.
Get real, man.
Yeah.
Okay. Because that's what I'm going to do to the top one too, to get rid of the fractions.
That should be equivalent to just multiplying the whole thing.
and
by
second one
zero.
has a fun factor.
That should be equivalent to just
A
multiplying
fun
the
factor.
entire thing by
That's
zero.
That's what I was thinking.
Say what?
But yeah, yeah. Oh, yeah. That gives
One
you-
is not a factor of the second
T
one.
and Q and C. R and C. Q and
Wait, did I write these in the wrong order? No,
Uh,
I didn't.
No.
Well, C's a bit, yeah.
No, one is not a factor of it. One is not a he means a root. Well, I guess one is technically. Oh, I see what he means.
Oh.
One a factor.
I know what the factor is.
Yeah, one is a factor of all these very flat ones. Took me way too long to get what I was trying to say. I think this is a fun root, is what I meant to say.
How do you write the oh, I can just do this.
X minus blah times
One has
x minus other blah. And these are monic polynomials at roots. So if you have a monic polynomial degree n and you have n roots, just multiply together x minus root, x minus root, x minus root, etc.
That's my favorite.
No,
That's my
the
favorite
ratio
kind of
is
root.
one of them is, I can't remember which right now. That one, I think.
The positive one.
Yeah, because wait, no, this one's less than 0, that's not it. So that one.
Golden ratio is less than 0, that would be concerning.
I know that it's an important number, but it's not the golden ratio.
It's the conjugate of the golden ratio.
That.
Yeah. Which probably has a special name that I can't think of off
Yeah,
the
I'm
top of
not.
my head.
I think aren't they both the golden ratio because they both satisfy or something?
Well, one is negative, one's positive, and if you wanted it to be positive for all of your next geometric problems to hold.
Well, I forgot that that was the golden ratio. Because usually when you find geometric things, there's like two algebraic solutions.
I was about to say something.
Yeah,
Yeah,
that's
and
what-
then you
it's
run
not
into
even
yeah, you
And
end
then
up
if it's
erasing your
irreducible,
geometry.
R.
It's also
It just it does some weird things.
No.
Yeah,
There is O and R, it has to be irreducible in C.
No,
Make a
First,
no.
the first example makes
Make a
No,
pentagram,
yeah, that's how
make a
it-
pentagram instead of a pentagon around.
What did
Ooh,
Do some.
I don't remember.
Alrighty, let's come back together and talk about this. Hi Lydia, if you're watching the video, stop, press play. Or normal speed. Okay,
Hopefully she'll like see you maybe.
so we'll start with the third one because that's what makes the most sense. So x squared plus x minus 2. Is this in what rings can we factor this into smaller terms? Lincoln?
All of them.
All of them! How can we factor this?
Negative x minus 2 times negative x plus 2.
You're awful.
I hate that. It's so fun.
Yeah, don't worry, I'm just ignoring him.
Yes!
X plus 2 times x minus 1. So we could say that it is irreducible over none of them. Reducible over all of them. Technically, when we say a polynomial is irreducible or reducible, we should say over the corresponding polynomial rings. Mathematicians can get a little bit lazy and say, hey, it's irreducible over the complex numbers. And what that means is it really means irreducible over the complex polynomial ring, but this is just kind of a shorthand for that. Alrighty, so that one's not so bad. X squared minus x minus 1. Emily Rose, what did you do for that one?
2x minus 1 minus square root of 5 times 2x minus 1 plus the square root of 5.
2x minus what now?
1 minus the square root of 5 times 2x 1 plus the square root of 5.
I already hate this because the leading term of this is
Divide
4x
by
squared,
4.
not x squared.
Divide by 4.
Divided by 4.
Or x minus square root of 5 over 2.
Yeah, just round 1/4.
Let's just how about we do that? There you go. Okay, so over which of these rings, Pete, is that polynomial going to be irreducible?
It would be irreducible over the rational numbers and the integers.
Yeah, it's going to be irreducible. This one is going to be irreducible over a couple of our rings, over the rational numbers and the integers, because there's no way to. These are just no. These are not rational numbers, but it is going to still be reducible over the complex numbers and the reals, because over the complex numbers and the reals, we can do this factorization. So finally, x squared plus x plus 1. Last one, but minuses have become pluses. Well, if we do a quadratic formula, set this equal to 0 and solve for x, we get a square root of 1 minus 4 all over 2, which is -1 plus or minus I root 3 over 2. So it's going to turn out this will factor into x. I'm not giving you all the chance to give me a more complicated version of this one.
Is it so much more complicated to pull the...
Yes, -1 plus I root 3 over 2
Just multiply by I.
times x by this -1 minus I root 3
I don't.
over 2. See, this is why I'm doing this by myself. This right here. So,
Really?
What?
so here it is. So, Matthew, over which of our 4 rings is this polynomial going to be irreducible?
Irreducible?
Irreducible.
I think it's gonna be probably both Q and Z and R also.
Yeah, this right here, that is not in Q, that is not in Z, that is not in R. So, turns out the only one of these where you can actually factor this into smaller terms is over the complex numbers.
So if it doesn't exist, then you just like straight up just make it irreducible, like automatically.
If what doesn't exist?
Like it doesn't even like live in Q, Z, or R. So
Yeah. Well, basically what we're saying is in Q, Z, and R, you can't do this factorization. Like,
right.
this only works over the complex number, so in Q, Z, and R, there's no way to write this as a product of
Okay.
smaller degree polynomials.
We're not talking about necessarily that factorization. We're talking about the polynomial original.
Yeah.
X squared.
This works as a factorization over C, but over Q, Z, and R, this is what you get. You can like do stupid things like, I'm Lincoln, I'm gonna factor out 1 from this. Or you could factor out like 2 and say it's 2 times a half of this polynomial.
Right.
But you can't break it down into a product of polynomials, both of which are smaller degree. Or technically, so that 2 polynomials, neither of which is a unit, technically, is what you really want.
Not the fun thing. The third one is a crooked square.
That one?
Yep.
Do tell.
In Z mod 3.
That's right.
Oh, is it now? Guess what I just came up with as a homework problem on homework 4. What ring did you say?
Z mod plus C X.
Okay, thank you.
3 Z.
Oh, thanks. I'll look into this. Well, you're giving me fun ideas. So,
Which one is that last one?
so what did we? So, all of these are quadratic polynomials because I didn't want to give you. I could have given you degree 5 polynomials or degree 20 if I was feeling, sadistic, but yes, if I was feeling like that. But what can we say about the relationship, do you think, from irreducibility over these various rings? relationships that we can draw here? Parker?
I would say that, well, we definitely, the complex numbers, if it's reducible in that, it doesn't mean it's reducible in the other ones. But I would think like if it's
True, both of those two examples would seem to break that.
But if it's reducible in the reals, then it's definitely reducible in the complexes. And if it's reducible in the quotients.
So in other words,
Oh,
irreducible over C implies irreducible over R.
Over the Q set, whatever you call that, is reduced. You can't put a Q there and not expect me to pronounce a quotient. If it's irreducible, if it's reducible
Parker,
over the rational.
Parker, at first I would agree, I can forgive that. By now, you've had enough time.
It's hard, okay?
So it turns out irreducible over the complex numbers implies that it's irreducible over the reals, implies it's irreducible over
No, other way. It's all the other way.
No, that's wrong.
No, that's right.
Oh, I'm sorry.
Oh, because it's irreducible.
Not
Irreducible.
Irreducible.
The other way doesn't work.
Irreducible.
Well, it works if it's reducible.
like, it's like
If it's
Oh!
reducible, it goes the other direction.
Yes, but
Reducible over C doesn't mean reducible over R because
you switch the
for
directions.
instance-
No,
Yeah.
you switch the
You switch
direction.
the directions of
If it's
the
reducible-
yeah, if it's
If it's reducible over Z, then it's reducible over
Q.
Q,
and
and
then R.
reducible over R, and reducible over
I'm glad we've had this discussion. Yes.
Okay.
Yeah, contrapositive is equivalent to the original implication. We can
Correct,
do that a
yeah.
lot. All right.
I love the contrapositive.
What? Should I draw a truth table to demonstrate this?
Yeah.
Lincoln.
Well, actually, this isn't technically true because some elements in CX are not even elements in R of X or Q of X.
This is true.
So-
Technically, Dr. Herschel, you can have something that's irreducible over that, like X minus I, that isn't irreducible over R because it's not an element in that polynomial ring. This is good. Let's say for an element in both respective rings. It's like being tricky with me, but he is technically correct. And that in order to have this implication, it has to be a polynomial over both of the rings that we're looking at.
But the contrapositive doesn't have that issue.
Oh, contrapositive doesn't have fine.
But it also
Because if
only
it's
includes-
reducible
Well,
in
that's
C.
what I mean. Because it's like implied.
Let's just
Yeah.
go with reducible.
So for instance, if we're looking at integer polynomials specifically, then this holds. And we're going to be mostly looking at integer polynomials going forward. All right, question. What's that equivalent to? What do we know about irreducible complex polynomials? Who remembers their complex analysis?
Oh, I didn't take it.
I remember.
Haven't had you Lincoln?
For a polynomial of degree n, it will factor into n linear terms.
Yeah, so what does it have to be if it's irreducible and can't factor into any terms of smaller degree?
It has to be linear or well, no, constants are units, so it has to be linear.
Linear. And it turns out this is the fundamental theorem of algebra. No, we're not going to prove that in this class. Take complex analysis if you want to see a proof of that. Turns out being irreducible over C means the same thing as being linear. Because every non-constant polynomial over the complex numbers factors into linear terms. Not super easy to prove, so we're not going to prove it in this class. It would take us like a week to actually get that. Plus, it's easier using analysis results than algebra results to actually prove that. But turns out that is the case. Are any of these arrows if no? Yes.
Does this get weird if you include if you're looking at non-algebraic numbers?
Non-algebraic numbers?
Yeah.
How so?
I don't know.
I mean, how does it get weird? I mean,
Does the
then you're still in here. I mean, then you're still probably in like this or that, but not these.
Yeah.
Well, you don't have to be in
Does the
R.
fundamental theorem of algebra still work for
Yeah.
non-algebraic numbers?
Yeah.
That seems like a contradiction.
Sure, it works. I mean,
Well, yeah, it's just, yeah.
how does that factor into linear terms over the complex numbers? Yeah, x minus pi times x minus e. It works for non-algebraic numbers.
Okay.
What's more interesting is when you ask, does it work for things like non-computable numbers?
Yeah.
And the answer is yes. But good luck finding examples.
I mean, technically, pi's not it.
Don't forget about saying that because of things like that one, we don't know whether pi, or we know that one of pi plus e and pi times e is is not algebraic.
This,
But
yep.
we don't know anything more than that.
Yep, the very strong suspicion is that neither of them are algebraic, but we actually don't know that. Pi plus e and pi times e.
Pi to the pi said about that too.
Pi to the pi is weird. I mean, we can say
The function
something
is-
about this being algebraic. If you want something that involves e and pi, but in fact, Gabriel and I were talking about this when we had math lunch last week. So, question. Can we find a counterexample for irreducible over R, but not the complex numbers?
Yes, I found one in physical space.
You found one in physical space.
It's right here, it's x.
What is it, like made out of foam letters or something? Sure, yeah, you can take one from the front page. You can also take something like x squared plus 1, even a little bit simpler. Something that is irreducible over the reals, but is not irreducible over the complex numbers. Because over the complex numbers, you can break it up into x minus I, x plus I. How about here? We find a counterexample for a thing that is irreducible over Q, but not irreducible over R. Eleanor?
The second example.
Oh, the second example. Okay, fine. X squared minus 2 also works as a kind of nice example here. Because over the reals, you can factor this into x minus square root of 2 times x plus square root of 2. But over Q, you can't do that. It's irreducible as is. All right, smarty pants looking at the front page. How about this one? Anybody think of an example of a polynomial that's irreducible over z but not q? Iris?
X squared minus 4 ninths.
X squared minus 4 ninths. I required this condition.
Oh,
That is
right.
I mean, that's not irreducible over z. It's not in that polynomial ring, so I'm not. I disallow your example. They should all work. Do you have it? Do you have kind of?
9x squared minus 4.
Right.
Yeah.
Oh, that looks an awful lot like x squared minus 4 ninths, huh?
But doesn't that factor to 3x minus 2?
Oh, wait, what?
Nope, sorry, it doesn't work.
Wait, so, oh,
What about like constant numbers?
There's.
Well, constants can't be irreducible by definition.
That's right.
Huh. In fact,
There shouldn't be.
there aren't any.
Oh, shoot.
That one does work both ways.
Oh. Okay, cool.
Oh, but the roots of the roots.
is it, does
Yes, Eleanor.
it have anything to do with the countability of both Q and Z?
Wow, someone's actually raising their hand in this class before blurting something out. What a novel idea. Does it have something to do with the countability of Q and Z?
Yeah, because those are the only two that are countable.
Yeah. I mean, it's not unrelated.
But wait.
I mean,
it's
these
not
have the same.
those-
I mean, these have the same cardinality
Yes.
though, and those aren't. And for those, it's not a double
Yes,
equivalence.
but both of those are uncountable.
Yeah, but not.
Q and Z.
Yeah, but they're the same sort of uncountable.
Yeah.
I mean, you're right that this fact is not unrelated to that. We're not going to get into that in this class. Like, our proof is not going to rely on that fact. But it is going to rely heavily on the fact that constructing Q from Z is Q is heavily constructed from Z. You're just taking quotients of elements from Z. Whereas going from Q to R, there's more going on. Although from R to Z, it's not actually that much going on, relatively speaking, either.
Well, because if Q and Z are both cardinal and countable, then you can construct some function going from one to the other. That's,
1 to 1 and on to. Yeah.
Which feels like that would be why it works, but I don't know.
Oh, well then. Sounds like a good question for Dr. Gabriel. So we're going to prove 2 things in this packet. One, we're going to prove this. Forward direction is pretty much immediate. Proving this implies that is a little bit sneakier. We're also going to prove this. Irreducible over R. Well, this one's not a double arrow. But if it's irreducible over R, it has to be linear or quadratic. Not the other way around, because there's many quadratic polynomials over R that aren't irreducible. X squared minus 4 as an example. But if it is irreducible over R, we're going to prove that it has to be either linear or quadratic. And this fact right here, as a sneak peek for next time, is strongly related to this property right here.
I saw this in the package.
Yep.
I have a hand wavy reason why.
You have a hand wavy reason why for this one?
Mm-hmm.
What's your hand wavy reason why?
Well, if it has 4 factors, say, then they were all, like if it has 4 zeros and they're all complex, then you can pair them up and the i's will turn into negative 1s.
Essentially.
Hand
Basically,
wavy, I said.
it basically comes down to the fact that if a real polynomial has a complex root, it also has to have the complex conjugate of that root as another root. So if a plus bi is the root of your real polynomial, a minus bi also has to be a root. Which is something I think we've mentioned but haven't proved. We will actually prove this in class on Thursday and use that to prove this property right here, and then we will also prove this property. And then after that, we will start looking at lots of different tests for when are things irreducible or reducible. Because it turns out things being irreducible, not an interesting question. Well, it's an interesting question to ask here, but fundamental theorem of algebra kind of fully answers that. Not a particularly interesting question here. This is a very interesting question. When are things irreducible over Q? That'll last us the rest of the semester. Have a good one, everybody. Parker,
Oh, yeah.
do your duty.
Okay.
Bye, Lydia.